Great, welcome back. Let's just do a couple more examples here. So if we're looking at this function, sine x over x squared plus 3, and just sort of looking at that as what happens as x goes to infinity, for sure the bottom is going to be infinitely large, but the top isn't. The top is just sort of oscillating around because we know the top is y equals sine of x, which is as x gets larger is just going to continue going up and down forever. So the question that we have is what would be then the limit as x goes to infinity? And so for this, I'm going to use an older theorem, the squeeze theorem that we've used before, which is sometimes useful for limits involving trig functions because we know trig functions, sine and cosine in particular, that those are bounded. So I know for sure sine x is always going to be between positive 1 and negative 1. I also know that x squared plus 3, it's always going to be something positive. No matter what I put in for x, x squared is positive and 3 is positive. So x squared plus 3 is positive. So I know that if I divide everybody by x squared plus 3, that my inequalities will all stay pointing in the same direction. So I'll make a little note of that on the side. So that's because x squared plus 3 is positive. So that's why I know that my inequalities will stay the way that they are. And so now if I were to look at the limit as x goes to infinity of all three, so the limit as x goes to infinity of negative 1 over x squared plus 3 of what we're actually interested in, sine x over x squared plus 3, and 1 over x squared plus 3. And for those two things on the outside, those are rational functions. I know that for a rational function, when the bottom has the larger degree, that its limit as x goes to infinity or negative infinity would be 0. So I have that the outer limits are both 0, and so by the squeeze law, I can say that, well, sine x squared over 3, its limit is between 0 and 0. So by the squeeze law, the limit as x goes to infinity of sine x over x squared plus 3 is 0. All right, another one. And this is another one that's sort of difficult when you first look at it and think about what could it possibly be. I see here I've got as x goes to infinity, I'll have x, which is going to become infinitely large, minus this square root, which will be infinitely large. You may be tempted to say 0 is the answer because you'd say, oh, infinity minus infinity, it must be 0. And the answer is maybe it is, but it doesn't necessarily have to be. Infinity minus infinity is indeterminate. It's possible that it might be equal to 0, it might be equal to some other real number, or it might not be a real number at all. And so I can't just guess at which it is. It's still indeterminate, so I need to do something to make it not indeterminate anymore. So my plan here is this. If we're thinking about what we currently have, I have x minus root of x squared plus 3, which you could think of as all a big fraction all over 1. If I were to rationalize the numerator, and so I would do that by multiplying top and bottom by x plus root of x squared plus 3. So if I were to do that, then what I would have in the denominator, of course, that would just be 1 over x plus root of x squared plus 3. And in the numerator, I'd have x squared minus the root of x squared plus 3 squared. In other words, I would have on the top, as x goes to infinity, the square root and the root would get rid of each other. I'd have x squared minus x squared. That would be gone. That would go to 0, and I'd be left with just a minus 3 on the top. And now we're ready to go because I can now see what's going on here. This is something where it should be pretty clear that it's going to 0 now, because as x goes to infinity, the numerator stays as a constant, and the denominator as x goes to infinity will become infinitely large. Just to make it really clear, though, I'm going to now say, and since x is infinitely large, since x is larger than 0, then definitely x squared square rooted is the same thing as x. So I'm going to divide everybody either by x or by square root of x squared as appropriate. So on the top, negative 3, I'll divide that by x. X, I'll divide that by x. And inside my square root, I'll divide everybody by square root of x squared. So x squared divided by x squared is 1, and 3 divided by x squared is 3 over x squared. And now it's really clear that this limit is going to be 0, because in the top, negative 3 over x, that goes to 0. 3 over x squared goes to 0. So we have a limit for the top, a limit for the bottom. The bottom's limit's not 0. We get 0 over 2, which is just 0. So in this case, our limit happened to exist, and it happened to be 0. Okay, so this one is sort of a trickier one if you're thinking about it. And it's trickier for a lot of reasons, because if you're thinking about what we currently have, it's definitely something indeterminate. As x becomes infinitely large, x is becoming infinitely large. As x is becoming infinitely large, 2 over x is getting close to 0, and so that means we're getting close to sine of 0, which is 0. So this is 0 times infinity, which again, you might be tempted to say, oh, that'll be 0. But that's an indeterminate form. It is not necessarily 0. We're going to need to do something. And this one is maybe the most surprising something that we're going to do. We're going to find our limit at infinity sort of in a backwards kind of a way. We're going to rephrase our limit problem. If I were to let x be 1 over u, so then as u is going to 0, specifically as u is going to 0, using positive numbers only. In other words, as we're approaching 0 from the right. So 1 over 1, 1 over 0.1, 1 over 0.001, and so on and so forth. As u is getting closer and closer to 0 and still being positive, x is getting larger and larger and larger. In other words, x is becoming infinitely large. So if we wanted to look at a limit as x goes to infinity, that would be the same as looking at our limit as u goes to 0 from the right. So I'm going to rephrase this. I'm going to say instead of x, I'm going to say it's 1 over u. And instead of sine of 2 over x, that would be 2 over 1 over u, which is 2u. And as I said before, instead of looking at limit as x goes to infinity, now we're looking at the limit as u goes to 0 from the right. Or in other words, the limit as u goes to 0 from the right of sine of 2u over u. And this has actually made things really nice for ourselves, because if you'll remember, we had a limit from before as to what happens for sine as it goes to 0 on the inside. I know that if this was sine of 2u over 2u, then the limit would be 1, and I could make it 2u over 2u if I multiplied top and bottom by 2. And now I've got something where the limit exists. I know from my earlier limit theorems, limit of sine of 2u over 2u as u goes to 0, that limit is 1. And 2 as u goes to 0, that's a constant function, so it stays as 2. So our limit actually turns out to be 2. So this is the place where things are, again, a little surprising, because if you looked at that and said infinity times 0, you might be tempted to assume that 0 would be the limit, and in fact, it is not. It is 2. And in fact, we could do a similar sort of one looking at x goes to negative infinity, which would be us going from u to 0 on the left. We'd find that limit is also 2. So for that graph of x sine 2 over x, it turns out it has horizontal asymptotes on both sides. And now the last thing for us to talk about are infinite limits at infinity. So not just stopping and saying the limit does not exist, but being more specific and saying the limit does not exist because the function diverges to either positive infinity or negative infinity. So suppose you've got a function, it's defined from some place off to the right, so a is some real number. We're interested in the limit as x goes to infinity of our function, and if that limit is positive infinity, then what that means is if we're looking at big enough x values, then our y values will become as large as we'd like. Or if the limit was equal to negative infinity, then for large enough x values, the y value becomes as big in the negative direction as we'd like. And you could say similar sorts of things about limits as you go to infinity to the left. So same sort of a thing there. So now that means if we're looking at a limit as x goes to infinity, positive infinity or negative infinity, you could have the limit exists. In other words, the limit's a real number. You could have the limit doesn't exist because the limit is positive infinity, or you could have the limit doesn't exist because the limit is negative infinity, or you could have the limit doesn't exist and is not either kind of infinity. It's just the limit doesn't exist. So taking a look at a couple of these examples, for A and for B, you could see for both of them that the function does not have a limit existing. And I know that because A and B, these are both rational functions. They are rational functions where the denominator has the smaller degree, the top has the larger degree. So I know that this function, the limit doesn't exist. If I wanted to figure out how to rewrite this function, I could, on the side, using synthetic division or long division, however you'd like to do it, rewrite my function. And I'm going to do that here quickly. If I take my function and I divide it by 2x minus 1, then let's carry out our division. Okay, so it looks like my quotient is 2x minus a half, and my remainder is a half. So if I were to rewrite this, I would say my little quotient that I have, my one thing divided by another, should be my quotient plus my remainder over my divisor. And so now it's pretty clear what's going on here. If I were looking at this function, I'd say as x goes to infinity, for sure that last term will get close to 0. The 1/2 will be 1/2, and the 2x will become infinitely large as a positive number if x is infinitely large and positive. So I could say for this limit, it's infinity plus a bunch of constants, which is infinity. And I'm going to do the same sort of thing for the second one. I have this function 5 minus x squared, and I'm going to divide it by 3x plus 2. So when I'm doing long division, flashback from days gone by, we have to put our powers from largest to smallest. and work our way from left to right. 3x going into negative x squared, that's negative 1/3 x. We multiply, that's negative x squared minus 2/3 x. And then we subtract. Negative x squared minus x squared is gone. 0 minus negative 2/3 x is 2/3 x. And then we bring down and repeat the process. So 3x divided into 2/3 x. That would be 2/9. 2/9 times 3x is 2/3 x. 2/9 times 2 is 4/9. And then now we just have to subtract. And so 2/3 minus 2/3 is going to give us 0. And 5 minus 4/9 is going to give me 41/9. So now I can say that this is the limit as x goes to infinity of my quotient minus 1/3 x plus 2/9 plus my remainder 41/9 over my divisor, which was 3x plus 2. And for this one, of course, that last term again is going to go to 0. 2/9 will stay as 2/9. And as x becomes infinitely large, negative 1/3 x becomes infinitely large as a negative number. So negative infinity plus constant, that should be negative infinity. And lastly, if I were looking at the sine function, as sine goes to infinity, this one I would just say that the limit does not exist, because we know what's happening with our sine graph. As x goes further and further to the right, it's continuing to oscillate. It's not approaching a finite number. It's also not becoming infinitely large. It's also not becoming infinitely large in the negative direction. So it's neither finite nor infinite. It's just oscillating, so we'd say that limit does not exist. The last little thing I wanted to mention about this, and this is something we'll talk about a little bit in curve sketching, is we could say for both the limits in part A and part B, they tell us a little bit something about the graph. Specifically in part A, as x becomes infinitely large, that 1/2 over 2x minus 1 gets closer and closer to being 0. So that means as x gets large, our y values get closer and closer to just that straight line, 2x minus 1/2. In other words, our graph will have an oblique asymptote. The line 2x minus 1/2 will be the asymptote that our graph will be approaching as it gets to the far left and far right. The middle, it'll be wiggling around and doing whatever it's doing, but on the far left and far right, our graph is getting closer and closer to the line y equals 2x minus 1/2. And for b, that rational function, as x gets large, it's getting closer and closer to the line y equals negative 1/3 x plus 2/9. So now we can formally state if we've got our function that is approaching some sort of non-horizontal line, then we call it an oblique asymptote or a slant asymptote. And for reasons of algebra, this really will only happen for a rational function when the numerator is exactly degree 1 more than the denominator. And that's because when we divide the numerator by the denominator, if they're exactly a degree 1 apart, then the quotient would be degree 1. If the numerator was degree 2 bigger than the denominator, then when we divided, we'd get a quotient that's degree 2. If they were 3 apart, then we'd get something where the quotient is degree 3. So the only way for us to get a quotient that's of degree 1 is if the numerator is exactly 1 degree higher than that of the denominator. So as we saw in the previous examples, if we wanted to find a slant asymptote, we just have to do that via division, and our quotient is our slant asymptote. So taking a look at this one, just sort of visually looking at it, I can see the top has degree 3 and that the bottom has degree 2. So I know that this definitely will have a slant asymptote, and I know that because I can rewrite this as a quotient. After I do my quotient, I'll rewrite this as quotient plus remainder over divisor. So I'll find out what do I get when I divide into 2x cubed plus 3x squared minus 2x plus 5. When I divide that by x squared plus 3x minus 1. Okay, so 2x cubed divided by x squared is 2x. We'll multiply. 2x times x squared is 2x cubed. 2x times 3x is 6x squared. And 2x times minus 1 is minus 2x. And now we'll subtract. And so when I do that, I'll have just minus 3x squared. There'll be no x's, and I'll bring down the next term, which is 5, and repeat the process. Dividing x squared into minus 3x goes minus 3 times. We'll multiply minus 3 times x squared minus 3 times 3x minus 3 times negative 1. And then we will subtract. And when I do that, I will have 0 minus negative 9x, which is 9x, and 5 minus 3, which is 2. So there we go. We found our quotient. We've found our remainder. And so what I know now is that f of x, my original function, can be written as our quotient plus our remainder over our divisor. And the one thing that I know is since what I'm left with, this little remainder over divisor, since that's a rational function where the bottom has a degree that's greater than that of the top, then I know for this term it's going to go to 0 as x goes to infinity. So I know that as x goes to infinity, that f of x will be approximating the line y equals 2x minus 3. And that'll also be true as we approach negative infinity. F of x will also be getting close to that line 2x minus 3. And that's, again, because that last term is going to be something that's approaching 0 as x becomes very large.